Good evening, everyone. Welcome to this G20 Math Seminar on the Mathematics of Information Science, Information Technology, the road ahead. See, the theme assigned to IISER Berhampur for G20 events is a theme of emerging technologies. It is very difficult to find a math speaker to give a talk in this theme, but we are very happy to have Professor Kumar Murty with us, who from University of Toronto, who will give a talk on the mathematics of information technology, the road ahead. So before I start the talk, I will like to say a few words about Professor Kumar Murty. Professor Murty is a well-known number theorist, and he has also contributed immensely to the areas of arithmetic, algebraic geometry, to the area of information sciences. And it was a very happy surprise for me to learn that Professor Kumar Murty has 2 US patents. Earlier, I was under impression that patents is not for mathematics people. So it was very happy surprise for me. Professor Murty is a co-founder of a few ventures like Prata Technologies and PerfectCloud. And he is very well recognized for his contributions to the mathematics and popularizing mathematics. Professor Murty is a fellow of the Royal Society of Canada. He is a fellow of the American Mathematical Society. He is a fellow of National Academy of Sciences, India, and many more. Also, Professor Murty has won several awards like Coxeter-James Prize, Inventor of the Year Award, etc. And recently, he received a large funding to set up from the Canadian Institute of Health Research for setting up a COVID-19 mathematical modeling rapid response task force sometime in 2020, I guess. Professor Murty has held several important positions throughout his career. These include Vice President position of Canadian Mathematical Society, Secretary of Royal Society of Canada, and currently he is the Director of Fields Institute. This institute is named after Saint Charles Fields, whose name bears the prestigious Fields Medal, mathematics equivalent of Nobel Prize. Professor Murty is a wonderful teacher. Some of us have been very lucky to have heard him giving seminars earlier in Chennai and Allahabad. And also we have had some fruitful discussions with him. He has written several books. So we are very happy to have you here, sir. Welcome you.
Thanks, Prem.
So with this, I invite Professor Kumar Murty to enlighten us about the role of mathematics in information technology. Thank you, sir. You can begin.
Okay, thanks very much, Prem, for the introduction and the invitation. I hope I'm audible. Both the sound is okay.
Yes, sir. Yes.
Okay, very good, very good. So I thought I would, as Prem said, this is supposed to be about the future, I mean, emerging technologies, but I thought it would be a good idea first to reflect on where we are today and how we got here and the role that mathematics has played. I think it's highly underestimated or poorly understood by many people, even in fields close to mathematics. And so it's worth just remembering some of the history that brought us here. The first slide, let me see if I can advance this. First, just reflect for a moment that I'm talking to you from Toronto and you're in Berhampur, and some of you are in Berhampur. I just did a Google search. It's close to 13,000 kilometers. How is it that we take for granted that I am not raising my voice? I'm just talking with my normal voice and sharing pictures also, and you're sitting over there and seeing all of this in real time. And you may be apt to say, well, that's the wonders of modern technology, but the wonder of modern technology is only possible because of the math that's underlying it. And without it, none of this would have been possible. So let's have a look at how we got here. I'm going to take first a little bit of a historical perspective before we get to the modern times. So from ancient times, it was under various thinkers observed that there is something very mathematical about the world we live in. Mathematical in the sense that you could describe phenomena quite precisely and predictably. This was noticed in the East and the West. Pythagoras, as you know, was more of a philosopher than a mathematician, but he realized this universe seems to exhibit mathematical properties. He thought somehow the planets, the heavenly bodies were kind of engaged in a kind of music of the spheres. The famous Indian astronomer Aryabhatta, he made many contributions to astronomy, but he's probably most well remembered for his contribution to number theory, what we call the Aryabhatta algorithm, which is the way of writing the GCD of two numbers as a linear combination of the two numbers. It's occurs in Aryabhatta. So these people were, neither of them were really looking at, starting from mathematics, they were looking at the universe that they lived in, and then came to the conclusion that that universe seems to be mathematical in nature. Then there's Descartes. Descartes, you see, is an interesting character because he was in a way a mathematician, but a lot of Western philosophy is built on Descartes' point of view. But Descartes was both from one point of view a rationalist, but also an idealist. So when he was 23, he says that he had a vision. So this is not a rational thing, it is just a vision, some sort of intuitive apprehension, that the universe is mathematical and logical. So so from that time, he sort of was, everything about his thinking was wrapped up in this idea of how do you make that precise, that how do you describe this universe mathematically? If it is really so that it is mathematical and logical, how do you describe it in mathematical terms? Now, of course, the universe, when Descartes says the universe is mathematical and logical, what do we mean by the universe? What is included? For Descartes, the universe is the physical universe. So the world of matter. And in Western philosophy, mind and thought are different from matter, which is different from the point of view in Indian philosophy, where the mind is and thought is kind of a subtle form of matter. So in his point of view, there's a dichotomy between mind and matter. And what he was saying is matter is subject to mathematical description. But what's interesting is that that puts he himself outside of the universe, because the vision that he had, the way he came to the point of understand, the way he came to the conclusion that the universe is mathematical was not a scientific or a rational process. It was a vision. It was sort of a revelation to him. And so that vision itself, to make this consistent, to make this logically consistent, has to be outside of the universe, at least the universe that Descartes was talking about. And also it's paradoxical that if you look at Descartes, one of Descartes' most important contributions, it is our ability to describe something geometric. Let's say you have a plane, and a point in the plane, to sort of describe that algebraically. And so what he did is he took something which you might think has a physical reality and turned it into algebra. So he paradoxically, he sort of took the physical to the level of abstraction through geometry. So now a straight line is not the thing that you draw on a piece of paper or on some grid, but it's the equation that describes it, and so on. So this was really a very, very important step forward in mathematical terms, that the concept of abstraction. And that is something we have to come to grips with. This is really why students of mathematics have difficulty when they first start, because of this principle of abstraction. But it's a common ingredient And whenever you try to mathematically describe a phenomenon, when you try to, for example, model the spread of the pandemic, the first thing you do is you abstract it. You don't say, give me the actual virus and I'm going to put, you say the virus is, you designate it by some symbol. And then you start looking at the way that symbol interacts with other symbols. And it's that set of interactions that you write down as equations. So what you have at the end is a set of equations, but that's an abstraction of the actual phenomena that you're trying to describe. Now that in hindsight, now it might seem like isn't that obvious? Isn't that the obvious thing to do? No, it is not obvious. That was a major step forward in the evolution of science and in the evolution of mathematics to abstract what you're trying to understand into a mathematical language. So when they say the universe is mathematical, what are they talking about? What sense is the universe mathematical? They mean basically that physical laws can be formulated unambiguously. So for example, we talk about gravitation. And some people say that Newton discovered the law of gravitation. Why do we say that? Didn't primitive people know from ancient times that gravity exists, that there is some kind of force? If you drop an object, it's going to fall. Wasn't that known? What makes why is it the attribution is given to Newton or other people? It's because they turned that physical observation into a mathematical statement by formulating a law. Not only is it the case that when you release an object on the surface of the earth, it falls, but there's a law that tells how quickly it falls. What speed, how long does it take? What's the equation of motion? So that's an actual mathematical law, and it's unambiguous, and it's completely explicitly stated, and it can be tested. So mathematics therefore gives a language for unambiguously representing, organizing, and manipulating information. This is really, really important point. That's why it has so much power. And we also rely on it because once you've represented it mathematically, you can use it to predict what's going to happen. It has predictive power. Moreover, if you combine it with what I said before about the abstraction, it often has predictive power on things that you didn't start with. You might have started by trying to model heat, the dispersion of heat in a room, and you realize that I can use the same equations to predict how pathogens are spread in a room. You see? So it has that the power of abstraction and the power of representing things in such a way that it gives a predictive power. These are really unique attributes of mathematics. Now, we're tempted, especially if you're philosophically minded, you're tempted to say, why is this the case? Why are there laws? Why should gravity work the way it does? Why are things so predictable? What happened to free will? What happened to freedom of spirit? Where is all that? So and we ask this question: why is the universe mathematical? There are 2 points we have to remember. Firstly, the universe that Descartes was talking about, and practically all of science talks about, is the physical universe. Secondly, why is the universe mathematical? The answer is nobody knows. That was true when the question was asked in ancient times. It's true today. Nobody knows. The famous physicist Wigner has this paper in the Communications of Pure and Applied Mathematics, the Journal of the Courant Institute. He calls it the unreasonable effectiveness of mathematics in the natural sciences. It's just so uncanny how effective it is. When space travel was being architected, Werner von Braun and others were trying to figure out how do you launch a rocket and how do you make it go to the moon. What people realized is you can predict with split-second accuracy how things are going, the dynamics of objects, the mechanics of objects in space, or even on the Earth. So it is uncanny in terms of how effective it is. But that's not to say it's a panacea for everything, that somehow mathematical description can do everything. It does have limitations. Let me tell you a very important limitation. So if you think of math as a language, and after all, it is a kind of language. I mean, I want to say something, for example, I want to talk about that straight line that we mentioned before, and I write down an equation for you. Well, I've expressed that line, which I could have drawn, in another way. So it's a kind of language. And as a language, it's worth trying to compare it with other languages. You know, for example, our spoken language. I'm speaking to you in English, or then you may speak other languages. How does it compare as a language with other languages? Well, it's well suited. This is what we've discovered in science. It's really, really well suited for describing our physical universe. Seems to work really well. And it has this ability to abstract, and it's precise. It's precise, totally precise. If you write down a mathematical statement that anyone watching considers imprecise, they'll tell you to fix it. Right? If you in a talk, if you try to say something and it's not precise, they'll say, what do you mean? To be a mathematical statement, it's got to be precise. And in this regard, I think the best way to understand math as a language with respect to other languages is to compare it with another beautiful language, namely music. Music shares a lot of characteristics in common with mathematics. And the first is it's unambiguous in terms of its expression. You see, when you write down the notes, whether it's in solfa or in sargam, when you write down the notes, it's unambiguous. You know, if you say re, it has to be re. And you may say komal re, or you may qualify it a little bit, but the note is very clear. And if you don't hit that note, anybody who knows the language will disqualify you. You say you're not singing correctly, or you're not playing correctly. So in terms of its expression, music is very precise. Just as mathematics, when you write down a mathematical statement, it's got to be very precise. It's unambiguous in what you're saying. But it's got another feature similar to music, namely what I call maybe I'll just point out here before I go on. It's got another feature and similar to music, namely, if an amateur takes a piece of music and plays it, and a professional takes the same piece of music and plays it, you can see the difference. You can feel the difference. But they're playing exactly the same music. I mean, the notes are locked in, and yet you can feel the difference. And in this way, math is also like that. The expression is unambiguous, totally precise, but there is something behind that unambiguous, totally precise expression that is not unambiguous or precise. It is something else, and you can see the difference when a professional is saying the same mathematical content and a beginner is saying it. You can see the difference. So really the comparison is quite apt, I think, between mathematics and music. The expression is precise, and behind it lurks a certain infinitude that can only be brought out by an expert. Okay, I also want to point another thing about language, namely what I call the uncertainty principle. This is a picture of Heisenberg. Heisenberg, you know, was a famous physicist in quantum mechanics, and especially we have the Heisenberg uncertainty principle that you can't know both the momentum and the position of an electron at the same time. Well, language also has an uncertainty principle, but here, in place of momentum and position, it's breadth and precision. You can't have a language that has both breadth and precision. If you expand the universe of ideas that can be expressed in a language, you do it at the cost of precision. And if you expand precision, you do it at the cost of breadth. So all of the languages of the world will take a position somewhere along the spectrum of breadth versus precision. So math has made a choice. Math has made a choice of precision. So it is very precise, but it did this at a cost. Namely, it's not suitable for expressing certain ideas. For example, feelings. Feelings are not best expressed through mathematical formula. It's really good for capturing quantifiable phenomena. Now, when I gave this talk before, actually, I gave this talk a few months ago in Bhopal, and one very bright person in the audience pointed out to me that, well, you just said mathematics is like music, and music can express feelings. So why is it now you're saying mathematics can't express feelings? Well, the point is music can express feelings if it's presented by the right person. I mean, the most feelingful composition sung by an amateur will actually evoke pain, I think, maybe on the opposite emotion of what was intended. So that latent content, the feeling or the emotion that is embedded in music can only be brought out by an expert. So again, but the score that is written down on the paper can't show the emotion. And it's the same with mathematics. And that's why when you see an expert talk about mathematics, you listen to, don't just listen to the math, watch them, watch their expression, watch their gestures, the way they move their hands. And they will say things like, this is a really beautiful approach to the problem, or this is an elegant solution. Now, and you can ask, how is it possible for something as precise and unambiguous as a mathematical formula or mathematical approach to something be beautiful or elegant? And again, if you want to understand that, I say, do the comparison with music. That's the best place to see how it can do that. Okay. So in terms of science, the success of mathematics in the physical sciences is enormous. We've just discussed that. We've seen that, how it helps us to predict things and model things in the physical world. But that success has been so enormous that, in fact, others have tried to imitate it. It has had a profound impact on society in general. Many other branches of inquiry that don't belong to the physical sciences. And for a while, it was the case that you can't be taken seriously in a field of inquiry unless you could connect it to mathematics. And so we find many new disciplines emerging as an attempt to bring mathematics into novel fields. And that is the task that's still ahead of us. That's still going on now. So let me show you a few cases of people who tried to bring math into their field of inquiry. This is Hobbes. Hobbes is an English philosopher, best known as probably the person who started political science. He has a famous book called Leviathan. Leviathan is a word for a giant. And in Leviathan, what Hobbes is doing is talking about the city or the state as legally being similar to an individual, only much bigger. So in other words, the city or the state or the country also has to obey laws, not just individuals. It's not that the individuals do things and then the country can do whatever it wants. It's also subject to law. So it's like an individual, but much bigger. How did he come to that idea? Actually, he came to it through geometry. Now, Hobbes is not a mathematician, was not a mathematician, but he came to that through geometry. Let me explain to you the story. He had a friend who was interested in mathematics, and around the time that Hobbes was about 40 years old, so not a young man, not an old man, but not a young man, he went to visit his friend. And this friend had a book open on his desk. And what was the book? It was Euclid's Elements, the book of Euclid, one of the books of Euclid. And the book was open to Proposition 47, which was the theorem of Pythagoras, or what in the West is called the theorem of Pythagoras. So Hobbes, being an intellectually curious person, saw a book open, he went to see what is written there. And he read the theorem of Pythagoras. And he said, this is impossible. I said, what's impossible? He says, this person says that if you have a right angle triangle, whatever the lengths of the sides of the first two sides, or the third one is completely determined by them, and it's given by an explicit formula. I said, yes, that's what it says. He said, that's impossible. Why is it impossible? So this friend, the mathematician, is asking Hobbes, why is it impossible? He said, because you don't know the lengths of the other sides first. How can you know the length of the third side? So he understood that this principle of abstraction that I had pointed out to before, that in fact, X can be X. X doesn't have to be 1 or 2. You know, beginning students have this problem. When you start talking about X, they say, what is the value of X? X is just X. And so the abstraction that in fact, you can call the length of one side A and the length of another side B and the length of the third side C, and they're bound by a relation, exact relation, seemed to Hobbes to be impossible. You cannot make such a general statement. So the friend said, okay, read the proof, read the argument. And Hobbes spent the rest of the day reading that argument until by the end of the day, he was astonished that he was convinced. And he said, this is magic. That the power of mathematics just astounded him, that you could at one time make this abstraction that worked not only for this triangle or for that triangle, but for all triangles all at once, all right angle triangles all at once. It's this whole business of abstraction that led Hobbes then to the idea of the city or the state can be an abstract individual. So political science was really born, at least in the West, where political science was born when Hobbes was exposed to this theorem in Euclid. So he was so impressed with this idea. It was not obvious that but it could be proved by systematic and logical reasoning. And he wondered whether all thought could be formulated axiomatically. So after that, he fell in love with geometry. Now, of course, here's the problem, of course, when you're not a professional mathematician, sometimes you fall in love with something, you think you understand it, but it can also lead you astray. But what he did anyway, he tried to apply this sort of abstraction, this method of systematic organization of society, and conceived of Leviathan, as I said. And he tried to make government and social institutions an object of rational analysis and politics science. I don't know to what extent he succeeded, but the origin is in his exposure to geometry. Now, as I said, Hobbes remained an amateur mathematician the rest of his life. He might have done a better job if he had had a deeper understanding of mathematics. He spent a lot of time in trying to square the circle and double the cube. You know, this problem of squaring the circle. Find by ruler and compass a square whose area is the area of a circle of given diameter. Well, you can't do it because pi is not algebraic, but he didn't know that. And doubling the cube, cube root of 2 is not algebraic. It is algebraic, but it's not rational. And so he didn't understand that. And so he kept trying to do that. And on top of that, it's maybe kind of a disease of people in certain subjects, that you get into debates even when you don't know what you're talking about. So he got into a debate with the mathematician Wallace about first mathematics, and then it went into theology and then personal things. And then Hobbes wrote this book, Marks of the Absurd Geometry, Rural Language, Scottish Church Politics and Barbarisms, of John Wallace, Professor of Geometry and Doctor of Divinity. So it had, the good thing with the story was that Hobbes was inspired by geometry to formulate his ideas in political science, but he went a little bit overboard in another direction. This is Montesquieu, a French social scientist. He also tried to figure out, is society structured on laws in the same way that the physical universe is governed by laws? So he tried to create what are the axioms of society? How do you organize society? So sociology, as at least as studied in the West, started maybe with Montesquieu's effort. He tried to understand these social factors, objects of science, subject to laws. So he had these social types, and as I said, it's probably the beginning of sociology. He also formulated this concept of three bodies of government: the executive, the legislative, and the judiciary, and the separation of powers between the bodies, and it's used around the world. But again, notice the peculiarities of their thinking. He was talking about a democratic government and these separation of powers of these bodies, but he didn't feel everybody was equal in society. So he advocated slavery and he had doubts about the abilities of women. Ethics, this is Spinoza. Spinoza tried to build a theory of ethics based on Euclidean geometry. So you can look, even today, go to the library and get a copy of Spinoza's Ethics. And it's written like a math book. Lemma, proposition, axiom, theorem. And the book is called Ethics Demonstrated in Geometric Order. Now, in fact, I think ethics cannot be written in terms of geometry, demonstrated by geometry, but I'm just telling you about the power that mathematics exerted, first in science and then beyond science, that everyone felt that if they had to justify their body of knowledge, make it look credible, they had to appeal to mathematics in some form or another. So Spinoza went to the extreme that anything that cannot be captured mathematically is illusion. So all of these people understood the power of abstraction to some extent, and they tried to formulate abstract concepts that were modeling the reality they were trying to describe. It's not the physical universe, but maybe it's the social universe or human behavior. And then they tried to analyze these abstract concepts and tried to find mathematical relationships between them. Okay, so that's history. Now, in our times, there is the whole, there is a fire alarm going around in my, can you hear me clearly, or do you hear a disturbance? Yeah. Yeah, okay. So
we can hear some noises as well. There is some
okay,
noise.
okay. So hopefully the noise won't be too loud. So I'll just keep going. Okay. So in modern times, the subject now has shifted from. It's still very important in describing the physical universe, but it's even more powerful in describing something that you can't necessarily see and touch, but nevertheless is affecting our world in a really big way, and that is information. So mathematics helps a lot in how information first is represented, how it's manipulated, how it's protected. And these are the main three pillars in which mathematics is sort of at the very foundation. None of the modern tools that we have for doing these things would be possible without math. And I might also say that if somebody who's not in math were to ask, what is the math that you use? And we try to tell them, they would say, that sounds really abstract. That would be that sounds really abstract. And it turns out that this whole concept of what is abstract, what is concrete, what is pure, what is applied, this is all, in a way, I consider it quite mythical. In fact, it is the abstract that gives rise to the concrete, but you have to go into the world of the abstract if you really want to reveal the power of mathematics. Okay, so I'm going to skip some slides because, by the way, Prem, can you tell me how much time I have?
So around 30 more minutes.
30 minutes. Okay, very good. Fine. So I'm going to skip some of these slides because I think this story is well known. Google is being talked about by everyone around the world, but really their question, the question that motivated the founding of Google is this question: is this point? How do you mathematize or quantify relevance? How do you give a numeric value to relevance? That's really what the Google PageRank algorithm tried to do. And so it's done. I'm going to, as I said, skip this because you must have heard many talks. You must have heard many talks about Google. Basically, you create this directed graph. Here's an example. You do a directed graph. You attach various weights to each node based on the number of edges connecting to it. And then you apply some linear algebra and you take the largest eigenvalue, and that gives you a weight to each node, and that tells you the ranking of those nodes, then tells you the importance of the pages. That's the page rank algorithm. Okay. And I say I'm only skipping this because you must have heard millions of talks already about Google. Okay, but let's talk about something which maybe you've heard less about. I don't know how many of you have thought about how it is that music plays in these portable players, like and at one time people used to use compact discs. I understand many of you do not use compact discs anymore. Maybe you use streaming services. In large-scale storage arrays, they've used DVDs or RAIDs. RAID is a redundant array of inexpensive disks. And all of these encode huge amounts of information. And the way they do it, because it's being sampled at very high speeds, the way they do it is that information has to be coded in a very efficient way. So it's not stored in a linear way, as you might imagine. It is stored in a way that I'm sampling. See, if I have a lot of information and I have time to peruse it slowly, then I can figure out what is relevant for me. But if I have very little time to quickly select what information I want, then very likely you're going to make mistakes. Very likely you're going to choose the wrong thing. So when we hear streaming music, for example, it's going at such high speeds. And so the selection is going to be either out of sync or incorrect. And so the way you store the information has to be such that the receiving instrument can correct for those errors. And the way you build in this error correction is by using something called polynomials over finite fields. Can I assume people know what a finite field is? Yeah, okay, no, I'm not going to define it, but okay, so looks like Prem is saying yes, okay. So polynomials over finite fields, and the way, and by the way, there's a modern version of this, which uses algebraic curves over finite fields. And what you do is you take a finite field of some cardinality, you order the elements, let's say x1 to xq minus 1, the non-zero elements, and then the code words, which is the elements that you use to represent information, are values of various polynomials of a bounded degree at points in that finite field. And you do this in such a way that you see, everything about error correcting is to try to separate a distance between code words, and you have to choose your degree big enough so that there is a separation, and there's an exact relationship of how many errors you can correct depending on what the degree of the polynomial is and what's the size of the field is. So this is a branch of mathematics called coding theory, where they work out how many errors you can do. I'll tell you, by the way, when these were invented in the 60s, Reed-Solomon codes, which are the simplest codes, they were invented because satellites were just becoming more common then, and we needed a way to receive satellite information. Now, satellite information is notoriously noisy because there's so much interference in space, so much electromagnetic radiation in space. So the transmission will be corrupted as soon as it reaches you. So you've got to have sufficient error correcting capacity to be able to translate that into something meaningful. And now you imagine you're getting pictures from as far away as Mars or Jupiter or the outer planets. It's incredible that the distance it's traveling through space, the amount of distortion it's subject to, and yet we're able to reconstruct the image. How is that possible? It's only possible because of polynomials over finite fields and being used in an error correcting way. As I said, now this has been generalized. We have better codes than Reed-Solomon codes using algebraic geometry, in which polynomials are replaced by functions on a curve, and these curves are coming from very sophisticated number theory, like Shimura curves or such things. Before I leave these coding theory, basically, what I should say that one of the big problems that people are facing now is to discover the quantum version of error correcting codes, because the fault tolerance in a quantum environment will necessarily have to be much higher And so people are looking for the next generation of codes for that context. Here is Roomba. I don't know in India if Roomba is used, so there must be some analog of this. This is a robotic vacuum cleaner. You set it up and it learns the shape of the room and then vacuums your room. It's all about computational geometry. So it navigates itself through computational geometry, and the kind of problems it needs to solve is what a computational geometry needs to solve is given endpoints, find the pair that has the shortest distance. So Roomba is able to figure out the shape of the room and navigate itself around. I think some versions of Roomba even know how to find a power socket and plug itself in when it runs low on power. Then we come to information security. So information security is one of the big success stories, I think, for the use of mathematics in information technology. So the issue is how do you establish a shared secret through an insecure medium? And this problem is very clearly an artifact of the modern world that we live in. So let me explain this problem again to you in other words. I'm talking to you, okay? You're listening to me, whether I'm in person or in Zoom. Okay, I want to say something only to Prem. Okay, I don't want, but I cannot go to him and whisper to him. Obviously, I can't. I'm in Toronto and he's in Berhampur. I can't go to his ear and whisper something. The only channel of communication is the one we're on now, where anything I say, you can hear. Everybody can hear. How am I going to say something that only Prem understands and nobody else will? So the classical solution for this is, well, Prem and I should have met beforehand and agreed on a shared secret. If I say A, I mean B. If I say 1, I mean 10. Something like that. We agree on a secret. So then I'm speaking as if I'm speaking publicly and you think you're hearing me, but actually I'm speaking in code and only Prem can decipher that code. Okay, but the problem is, what if I don't have that opportunity to go and we agree on a shared secret? And if you think that's abstract, it's not abstract. If you want to order a pizza online and they want your credit card number, you can't go to the pizza vendor and agree on a secret on how you're going to encode your credit card number so that only he or she understands it and nobody else does. If you could do that, you'd go to the store and get the pizza yourself. So establishing a shared secret through an insecure medium such as the internet is a fundamental problem that it's a modern problem that mathematics had to solve. And to do this, there's no such thing as perfect security. All security can be broken eventually. So you only measure security through what's called how long we think it takes to break it. So the computational difficulty of decoding it. By the way, be careful about the word coding and encryption. They're two different things. In coding theory, we're not trying to keep anything secret. We're just trying to have a representation of information that enables us to reconstruct it with a certain number of errors. In encryption, we're trying to keep the information secret. So there are two different goals, and so there are two different approaches. So here in information security, we want to keep the information secret. And so the way it's done is to develop an algorithm that depends, the breaking of which should depend on the solving of a mathematical problem that we consider to be computationally infeasible. That is, it will take you too long to solve it. And the examples that are used are factoring integers. So the RSA system, for example, is based on the difficulty of factoring integers, especially integers with 2' factors, or maybe computing a discrete logarithm in a finite cyclic group, finding the shortest non-zero vector in a lattice, and so on. There are some problems like that. Now we know that if a quantum computer is ever built, some of these problems become easy in the sense they can be solved in so-called polynomial time. But I believe the shortest non-zero vector in a lattice still cannot be solved in polynomial time even on a quantum machine. So information security is built on mathematical algorithms, mathematical paradigms, and you measure security by the difficulty of solving a particular mathematical problem. If you make it computationally infeasible in reasonable amount of time, then we consider it to be secure. Okay. And there's a lot to say in this, but I want to move on to what I think is the most exciting thing forward for us, and namely how mathematics is going to impinge on the life sciences. I think this is really the new frontier. And I would say it's similar to the relationship that evolved between mathematics and physics in the 20th century, when relativity and quantum mechanics and these things were being developed. It was really quite an excitement, the combination, the interaction between physicists and mathematicians. And I think we are now in that kind of state of affairs for relationship between mathematics and life sciences. So if you're a budding mathematician looking for how to use your abilities outside of traditional mathematics, I would say look to the life sciences. Or if you are in the life sciences and wondering how you're going to make that breakthrough on the fundamental problems of life sciences, try to learn some math. These two communities have a lot, I think, to offer in the decades to come. The big difficulty is not in the difficulty of their subject. The subjects are difficult in a way, but that's not the hardest part of this. The hardest part of it is we don't speak each other's language. People in math don't understand what the life scientists are saying. People in life sciences don't understand what the math people are saying. This became really clear during the pandemic when we were all forced to sit at the same table because everyone had to participate. I was co-chairing the modeling table here in Ontario and listening to virologists or other people, and they use a different language, they have a different expression, different kind of ways of saying things. But you have to bridge that gap, and if you don't bridge that gap, then you're going to miss a huge opportunity to innovate and take both subjects forward. But in asking this, by the way, it's interesting that Schrödinger, the famous physicist of Schrödinger equation fame, gave lectures, I think it is in Ireland. Very brave of him to give lectures at a conference in biology. And the subject is, what is life? So he was at the height of his fame at that time. A lot of success in describing the physical universe through mathematics. And when I say physical universe, not only the visible, but the world of the quantum too. But he had a question, is the living universe also describable in this way? Is there a way to think of living beings in mathematical terms? So, but that's really hard. Gives rise to really fundamental questions like, what's the biological counterpart of force? You know, how do you model functional and non-local interactions? I mean, something happens here and it has an effect over there. So, and then how do you do self-organization? That is, somehow cells come together and they start learning about each other, and then they start working as if one unit. You know, this whole business of self-organization. And then emergence. How do you model emergence? Emergence, you see it even in what's called swarm intelligence. You know, a swarm of birds come and land at a water pond, and they're drinking water, and then somehow suddenly all of them take off and start flying again. So how does that happen? And somehow the collective seems to know something that the individuals don't know. So there is something else going on in living systems, and we're still struggling to find what is that language to express these concepts. A lot of advances have been made, largely because of the work in AI and machine learning, but still lots remains to be done. They're still in quite primitive state, I think, relative to what needs to be done. So if information technology of the past was about reading the physical universe, reading and manipulating the information of the physical universe, and information technology of today is about representing and manipulating the information we are generating, the IT of the future is about reading and manipulating information in living systems. How do you represent them? How do you read them? How do you manipulate them? And organisms, living organisms, they differ from inanimate matter because they possess coded information, algorithms that can be triggered by various things, and or they may not be triggered. So it's not a deterministic environment. So, for example, mathematical neuroscience tries to model neuronal activity. And in neuroscience, the main problem is how does the nervous system process information? It's a really hard question. I'm going to come back to this in a little bit because I find this particular question really fascinating. Population genetics, how do mutations and selection, how are they propagated in a population? What's the trigger? Why does a certain gene start expressing itself in a population and in other situations it doesn't? The dynamics of disease, we learned a lot during the pandemic. A lot of new ideas were formulated and came up in understanding the last pandemic, and it's going to it has changed the subject of epidemiology. It's become new mathematical tools have been introduced in the dynamics of diseases. Now, I want to talk to you a little bit about a field called systems biology. So systems biology is let me take a step back and talk about your computer system. Okay, so in your computer system, at least if you're using just your laptop, but even if you're using your laptop, you also need a printer. If you want to print out some documents, you need a printer, and maybe you have your cell phone. You have your handheld, and you want the cell phone to be able to talk to your laptop, and you want the laptop to be able to talk to your printer. So now suppose I've set this all up and it's working, and then I realize I want a new laptop. Okay, I want a new laptop. Do I need to throw everything out? Do I need to throw the printer out and the laptop out and the cell phone and get completely new components? No. If you did, then you'd say you have a pretty dumb system. I should be able to change my laptop and then plug it into the system, and the system will still work. The printer will recognize the new laptop and the cell phone will recognize the new laptop. This is the systems approach. I have components, functional components of a system, and I can plug and play. Okay, I can remove one component and plug in another component, and the system still works. Now, systems biology asks, is the living cell like that? Is the living cell a system where you can plug and play, you can remove components and insert other components? This started actually, I think it was at MIT. And the question they were asking was this kind of question. When somebody has cancer, they sometimes get chemotherapy. Chemotherapy is to irradiate the tumor with these very toxic chemicals, and thereby hoping to kill the tumor. But these chemicals are so toxic, they kill healthy tissue too. So the result is people who go through chemo, does have some positive effect, but it also creates lots of toxicity, lots of side effects that some people even die from the side effects. So the question was asked, is it possible, can I create a living cell so that when this living cell comes into contact with a cancerous cell, it becomes luminous? So this doesn't exist in nature. But if I think of the cell as a bunch of systems which is executing a function, can I change its function? Can I get it to execute an algorithm? Can I plug and play? Can I take out pieces of the cell and put in other things from other cells? I'm not bringing anything to life. I have to work with living cells. But is it possible? So this whole subject of systems biology started off by looking at a cell as a system, realizing that information is not just in the genetic matter in the nucleus, but all through the cell, and that the cell can be analyzed as some combination of functional components. And we want to predict and control the behavior of the system and even change it. So what I told you, that's systems biology. What I was telling you actually is synthetic biology, where now you ask, can I change what the living cell does? Can I engineer a living system? So this is a very hot subject. I mean, a lot of people are working on it, and you can imagine what it could do for medicine if you could create synthetic agents that executed an algorithm inside the body. It would make precision medicine a lot more possible. So this is a really, really exciting area people are working on. But then when you go, but we're still in the world of matter. We're still in the world of physical matter. What about the more difficult world of the mind? What about emotions, and what about intelligence and consciousness? Firstly, the problem is, what is it? What is intelligence? You see, we talk about artificial intelligence. What is real intelligence? We keep talking about artificial intelligence because we don't know what real intelligence is. How do you find meaning? And what do we mean by meaning? And what is consciousness? These are all problems now that used to be, at one time, maybe the realm of spiritual discussion, maybe later the subject of philosophical discussion, but is now the subject of scientific discussion. And where there's science, there's math, because you can't have a scientific discussion without math. There's also this concept of organoid intelligence, that somehow cells organize themselves into systems, and these are cell cultures made from stem cells, and they simulate organ functionality. So they're not an organ, but they behave as if they were an organ. So this is a subject of which is still evolving. Even the definition is not clear. Okay, now we want to go back to a very famous mathematician, John von Neumann. Hey, by the way, please stop me if I'm running out of time. Just wave your hand or something. If I see you waving your hand, I'll know I'm running out of time. So this is John von Neumann. And von Neumann in the 50s, I believe, gave some lectures at Yale University. And at that time, I think he was already quite sick. In other words, he was maybe, he was not well. But his lectures were on the called Mathematics in the Human Brain. Actually, you should look for a little booklet that he published based on those lectures. It's called The Computer and the Brain. So in the 50s, our concept of a computer was still very primitive. You know, what we hold in the cell phone would occupy maybe an entire floor of a building, maybe an entire building. So he's talking at a very early stage of computer science. So he compared the human brain to a computer, but wondered why the analogy didn't quite fit. Because this computer that we have here seems to be vastly superior than the most powerful computers that people could build at that time. And he argued that it came from really two different things. One is parallelism, that it could do distributed computing in a very efficient way that people hadn't figured out until much later. But the other thing is what he called the nature of mathematical calculation. So I think I'm going to maybe say very briefly what I'm going to skip some slides here, but the problem that von Neumann was trying to address is this. This computer is analog. It's not digital. It works on certain chemical processes, chemical and electrical processes. Analog computers make mistakes. The error in making analog calculation is very high. So if you do a calculation using an analog machine that involves several stages, first I calculate this, then I use the result to calculate this, then I use this result to calculate this, within 2 or 3 steps, the result, the answer you get will be useless. The error would be compounding so fast, the answer you get would be useless. And yet, this analog computer does solve such problems. It does solve problems that involve iterated calculations over how are we able to do that? So what he figured out is that the architecture of the brain is very different from that of a computer. He says that it has low logical depth. So the serial operations are very few. It's more the distributed simultaneous calculation that is more prevalent. So biological calculation, according to von Neumann, seems to be more horizontal. And this horizontal nature of biological calculation is what saves us by eliminating the problem of compounding errors. Moreover, he says the language of the nervous system seems to be of this kind, but he also says that the nervous system seems to use a radically different method of notation, which is stochastic, not the positional system. You see, again, I told you before about rapid sampling. You know, when you're streaming information, it's coming so fast and you're going to make a lot of mistakes. So you use error correcting codes to compensate for that. But our neurons are fighting, like millions of neurons are fighting so fast. How are we able to process that information and say anything sensible? The answer, according to von Neumann, is that the information is being represented in a radically different way than the way we represent information in a digital machine. It's stochastic. And that we're reading information in statistical properties of the message. And so the implication for math, he says, is that the math that we know and use today may in fact be a secondary language derived from the primary language of the nervous system. So here's the problem. Is it possible then to build a mathematical model of the human brain? If we succeed in that, that will radically alter the way we construct digital computers. It may also radically alter our views of intelligence and consciousness, and most importantly, underlying all this, what it means to be human. Okay, thanks. I hope I maintained the time.
Let's thank the speaker. So, sir, can we have some time for questions?
Sure.
Yeah, so online audience first, questions. Second control, somebody has raised hand. So any question from online audience?
It will be good.
No? Okay. Any question from audience here? For question, I think you have to come in front and ask because we don't have a mic. So, any question, guys?
Okay, looks like they're all happy.
Okay. So I have a few questions.
Hmm.
In the beginning, you said that difference between music played by a professional and by a beginner, and same thing like when mathematics talk is given by an expert and a beginner, there is some difference one can make out. Is it because like we are moving from a discrete to continuous thing? How smooth you do, better people appreciate, something like that?
No, I think there is something, maybe let me call it something irrational, something else that's happening in communication. It's not what you're seeing, it's not what you're hearing, it's something else that you're feeling. It's really the case. I mean, look, think about it. Every time we communicate, why sometimes you find it's very effective and sometimes it's not very effective. It's not, you can play a tape recording and you don't get the same thing. It's something else that is not tangible that is being communicated. And it's the case in math, it's the case in poetry, it's the case in music, it's the case wherever human beings are involved. Are the deepest part of our communication is not verbal, it's not physical at all.
So there is some sort of breaking or jump. That's why we are not able. I mean, if there is no long jump, then it is very effective, I guess. And when jumps are there, then
maybe I'm not sure. I mean, in math, I keep telling people slow down. When you're giving a math talk, slow down, because it takes time for people to assimilate what you're trying to say. And you find beginners go blah, 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 they're really fast, thinking that I can read their mind. I can't read their mind. I'm trying to read what they're writing on the board. But in fact, if we get into the flow, yeah, then I can read I can sort of get the sense of what they're trying to say, which is not verbal. But the deepest part of communication in any context is not what you see or hear. There's just something magical happening behind the scenes.
So another question I had, sir, about this epidemic predictions.
Yep.
The mathematics we use there, is it mainly data analysis or something more than that?
No, I think there were different kinds of modeling. One is some of it is data driven. So there we actually invented new, I think, formulated new ways of looking at data that helped us make better predictions. And some of it is deterministic modeling, and some of it is stochastic modeling. So those come up into systems of differential equations, and then you analyze them, you solve them, and you see how, and you can plot them so precisely you can predict on which day you think a certain wave will end. So it's different. So it's a combination of those different methods.
Okay, sir. So yeah, it was a very wonderful talk.
Thanks.
And we hope to have you here in our campus sometime.
Yeah, that'll be nice.
A physical talk and interaction after that, I think, has a completely different meaning.
Yes.
So
Okay.
let's again thank the speaker. Thank you, sir.
Thanks. Bye.
Thank you, sir.
Thank you. Bye.
Hey.
Bye.
Hello.